Okay, so this is actually theorem 334 from last time. So what you have here is a non-empty set, and R is an equivalence relation on A. So here's some things about this. For all X in A, the equivalence class of X, or the equivalence class of X is contained in A. I'm going to use this notation from here on out. And X is in its own equivalence class. So in particular, what this says is no equivalence class is empty, because the equivalence class of X contains X. When you take the union over all the equivalence classes in A, all the equivalence classes, then you get all of A. So in other words, what this kind of says is every A is in some equivalence class. X is related to A, X is equivalent to A if their equivalence classes are equal, if and only if. And finally, if you have some element of A and it's not the equivalence class of X, then the equivalence class of X and the equivalence class of A completely miss each other. You have an empty intersection. So this is fundamental, and it leads to an important theorem that we're going to get to in just a moment. Number one. For all X in A, the equivalence class of X is in A. Well, this is the set of Z in A such that Z is equivalent to X under this relation. By the very definition of what an equivalence class is, this is a subset of A, because a priori this is stuff in A. Everybody okay with that? So that's not too also, so X is in its own equivalence class because X is equivalent to X, right? And so that's the last statement. What about 2? The claim here is if you take the union over all the equivalence classes, you get everything in A. Well, let's see. This is an equality of sets, isn't it? So I need to show contained both ways. Each one of these things is contained in A. So the union of all this garbage is contained in A. Okay with that? What about the other? Notice that by 1, X is in the equivalence class of X. Yes. X is in its own equivalence class, which is contained in the union. This is one equivalence class, so it's contained in the union of all equivalence classes, because one of these equivalence classes is this one. So any X and A is in here. Number 3 says that X and Y are related if and only if they have the same equivalence classes. Right? Okay, So this is an if and only if. There's two directions to show. Suppose that X is related to Y. We need to show that these two sets are equal. Okay, well. Let's show that the equivalence class of X is contained. And I want you all to pay attention to this, because maybe you can help me on the next one. I want to show the equivalence class of X is contained in the equivalence class of Y. So let's let C be in the equivalent class of X. What does that mean? What does it mean for Z to live in the equivalence class of X? Right, it's related to X, right? That's what it means. But what do I know about X and Y? That's right, they're related to Y. Z is related to X, X is related to Y, so what do we know? Since R is transitive, Z is related to Y as well. But what does this mean? If Z and Y are related, this means that Z lives in the equivalence class of Y. Therefore, the equivalence class of X is contained in the equivalence class of Y. Somebody help me out here. What else do I technically have to show? I've got to show the other. Can somebody tell me why I'm really kind of done? You can just say something. That's right. Just do some little role reversal with X and Y, right? It doesn't make any difference. Now this is an if only if. I've just done the error of one right. How about this? Now suppose. I think this one might be easy. So, how are we going to show? We have the equivalence class of X is the equivalence class of Y. Now I need to show that X and Y are related. Well, right, X is in the equivalence class of X by part of Y. So X is in the equivalence class of X, which turns out to be the equivalence class of Y. Right, because that's our assumption here for the other arrow. Hence, because what does it mean for X to live in the equivalence class of Y? It means X and Y are related. And so, done there. Everybody okay? This is an important one here too. What this one says is if A is any element of my original set A, and A is not the equivalence class of X, then the intersection of them is empty. Right. Okay, any ideas on how to prove this? Yeah,
Wouldn't A not be X's relationship that the intersection of two relationships is empty? I feel like A not being in the X relationship. It's like,
well, okay, so let's suppose, I mean, I think you're on the right track. Suppose this is not empty. Right? Let's suppose this is not empty. What does this mean?
there's some X, there is a certain X.
If it's not empty, there has to be something in A that looks both in the equivalence class of X and in the equivalence class of A. Everybody okay with that? But doesn't this mean that Z is related to X? And this also means Z is related to A. But this is symmetric. I'm sorry, complexity. What I want to say. I want to get those two. Hence. And again, by reflexivity is X. So A is equal to plus X. By the way, what did I do here? What technique did I use to prove this? Well, you could couch that way, but really, what did I do? I assumed not this and got not that. Right? Anybody remember what that is? Contrapositive. Okay, any questions on that? Okay, this is a giant theorem. I'm digging on this theorem. Because basically, what this theorem shows you, and this is the reason that, well, one of the reasons I should say, that equivalence relations are so very important, is equivalence relations are basically partitions, right? So what this theorem is basically going to tell you this is, if I give you an equivalence relation, then it gives a partition of the set. And not only does it work that way, but if I give you a partition of the set, it gives you an equivalence relation, right? Let me give you an example. Here's a partition of the set of people in this room, not counting myself. All right. The partition is people on this side of the room and people on that side of the room. So from your perspective, I'll call this the right and the left. Okay. That's a partition of this set, right? Nobody in here is sitting on both the right side and the left side, right? Now, could anybody describe to me how that would give rise to an equivalence relation on the people in here, not counting myself?
Say the people sitting on the given side of the ring must put one to the other sitting on that side.
That's exactly it. That's exactly it. I am going to declare any two people on this side of the room equivalent. Any two people on this side of the room equivalent. And that's your equivalence relation. Everybody is equivalent to themselves. You two are equivalent, so you two are equivalent, and transitivity holds as well. And basically, that's it. An equivalence relation always gives rise to a partition. It's basically the equivalence classes. And any partition that you could ever think of, no matter how you divide up the room, gives rise to an equivalence relation. So let me put this down formally. Let A be a set. Let me say non-empty set. Then there's a one-to-one correspondence. Between equivalence relations on A and partitions of set A. More precisely, if P is a partition, fancy P is a partition node. Then there is equivalence relation on A. And this theorem is really gonna, not only is it going to be fact, I'm going to explain to you how it works, how the correspondence works. And there's equivalence relation tilde sub P on A such that the equivalence classes under this equivalence relation correspond to the sets in P. Furthermore, any possible equivalence relation on A is of the form exactly. So what this theorem says is take a non-empty set. If I walk up to you on the street and give you a non-empty set and a partition P, then there's equivalence relation such that the equivalence classes are exactly equal to the partition that I gave you. Not only that, if I walk up to you on the street and give you any equivalence relation, it's of this form, which is really super cool. So let's prove this theorem. This one's a big. And in fact, let's give you partition. So I'm going to start here in this part of the proof. I'm gonna suppose that I'm given the partition, I want the equivalence. We define. I'm gonna do it just like Daniel told me. Here we've got a partition. This is me breaking up, my set. So this is not part of my proof, maybe some visual aids. What is a partition? Well, remember, it's like a giant puzzle with pieces in it. So there's my partition of my set A. I'm going to find relation on A via, I'm going to say that X is related to Y if and only if. Anybody want to guess? If and only if X and Y are in same element of partition B. Subset of that. Because remember, the elements of the partition are these subsets. So X and Y would be, under this partition here, would be related. But X would not be related to T or Z, Y would not be related to T or Z, and T and Z are not related. Right, okay? So that's what my relation is. Now, I guess I need to prove that this is in fact an equivalence relation. One, note. X is related to itself because X is in the same subset of X, right? Two. Everybody okay with that? If X and Y are in the same subset, then Y and X are in the same subset, right? And finally, Y are in same here. And there's a little something here. What does it mean for X and Y to be related? Well, it means they're in the same element of partition, right? And Y and Z are related, so they're in some other piece of the puzzle. Everybody agree with that? Where Q and B are just two elements of partition. What does this mean? Where does Y live? It lives in both Q and B. So what can we conclude? Q and B are the same because this is a partition. Remember, that's one of the rules of partition. Any two subsets are either exactly the same or there's no overlap. There's an overlap here. So X and Z are both in the same set, therefore and this transit. So is Okay, any questions? So far? Now, what else should I really? Need to show here? Well, right, but I really probably need to finish my thought on this. What about proved here? If I've got a partition, then this thing sets up an equivalence relation. I need to show that the elements of partition are precisely what the equivalence class is. Isn't that what I said? The equivalence classes correspond to the sets of B. I claim classes on this equivalence relation. So I claim, now that I've set up this equivalence relation, I claim that the equivalent classes are precisely the sets of B. So what's left? For PIs are so these are the subsets. Recall what this means. PI intersect PJ if I is empty. If I is not equal to J, the union of PI is equal to A, and no PI is empty. So these are the elements of my partition, right? I claim that these are the equivalent classes. So, but X being A, then the equivalent class of X is the set of Z and A such that Z which is the set of Z and A actually, let me. Since P is a partition and X is an A, X is in one of those PIs, right? That's what it means to be a partition. Because everything in A has to be in one of these. Right, okay, so far? Okay, so the equivalence class of X is the set of Z and A such that C this is all the elements of A that are in the same subset as X is, which is precisely PI. For some. And so there you go. So these are the set of equivalence classes. PIs are the set of equivalence classes, and each A is in some PI, so this exhausts all of them. Everybody okay with that? For the other part, I'm going to appeal probably the previous theory. Now, the other thing that we have to do is basically what we've shown so far is if I give you an equivalence relation, I'm sorry, if I give you a partition, use that partition to make the equivalence relation, and that's exactly what you get, the equivalence bias. On the other hand, suppose you have some equivalence. Call it tilde on A. And I want to show that this leads to a partition of the set. Well, by theorem 334, shows that set of equivalence classes uh, union it's the union of all equivalence classes A, and each equivalence class is not empty because, in particular, X is in the equivalence class of X. Uh, uh, X and Y are either identical or distinct. And so if you throw out the redundancies in here, you get a disjoint union equivalence classes equals A. So that's the other direction of the correspondence. Depending on the previous theorem. Any questions? Okay, let me give you an example. We talked about decks of cards. Here's we declared that two cards were equivalent if they had the same rank. We declared that they're equivalent if they had the same suit. By the way, what happens if I declare in a 52 pack of regular playing cards? What happens if I declare the two cards are equivalent if they have the same rank and suit? What's in there?
Cards, so.
That's right. That's the equal equivalence relation, right? Each card is equivalent only to itself. There's only one jack of hearts, right? So if they have to match in both rank and suit, that's an equality. Here's another one. Let's let A. So here's the totality of the integers. Yeah, all of it. In I'm going to call this related 4. let me talk you through this part. I'm gonna declare the two integers are equivalent, related, if their difference is divisible by 4. And I know that there's some of you in here that are fast modular arithmetic. This is mod 4 arithmetic, if you like, if you're interested in this sort of thing. So, is n equivalent to itself? Sure it is, because 0 is divisible by 4, right? Suppose that n and m are related, that means that n minus m is a multiple of 4. Doesn't that also mean that m minus n is multiple of 4? Right, in fact, all you do is change the sign here, still divisible by 4, and so m is equivalent or related to n. Right, so it's reflexive. Suppose n is related to m is related to j. Right, that means n minus m is multiple 4. It means m minus j is multiple 4. Add them up. N minus j is multiple 4. So this, everybody comfortable with this being an equivalence relation? So for the equivalence classes, there's just not enough color in the world. Oh, let's just pick something. -3. Who's in -3's equivalence class?
1, 5, -7.
Right, -7, or here somewhere, 9, right? So it's every, you just take 4 steps, right? What's in the equivalence class of 0? What's in the equivalence class of -1? -5. What's in the equivalence class of -2? What's +2? So basically, you have 4 equivalence classes here, don't you? Because you see that what happens is you eat this up in steps of 4, so only in 4 steps of equivalence classes, I've got everything eaten up. Everybody agree? So my equivalence classes actually here look like this. There are your 4 equivalence classes. Everybody okay? Which one does that belong in? How do you tell? It's a count. How do I know this class?
Or take them.
That's exactly right. So here's the way to think about this. What do these all have in common? Look at all these numbers. What happens if you divide, use the Euclidean algorithm and divide this by 4? What remainder do you have? Always 2. Eventually you divide this, what remainder do you get? 3. How about this? Remainder 0. And this is remainder 1. So to find membership, even though it goes outside of my list, take your number, divide it by 4. By the way, 8675300 is divisible by 4, right? Because it ends in 00. That means it's equivalent to 9, and 9, actually I can see it right there. So we'll have one on that remainder. Right, okay. Notice that this is sort of like odd and even, only it breaks it up into finer pieces, right? Notice that everything in these two are even, everything in these two are odd. But you're going further by telling them part by division by 4, what their remainder is. Any questions? Okay. Here's another kind of relation. So equivalence relations, they're the bomb. They're a big one. But here's another important thing. Often in mathematics, of course, you see that a lot, especially in science courses. Everybody likes to attach size to something, right? You measure things. Is this big? Is it small? Do you maximize something? Things like this. So ordering relation is kind of about that. We're going to compare things by size in some sense. There are many ways we might think about what size is as well. So I am going to appeal to your intuition first before I give you something formal. Let me kind of give a picture about this. It's still something undefined, yeah, but. This is like the less than or equal to that probably you first learned when you first started tackling numbers. Things like this. Basically, if I look at my integers, they're kind of conveniently, aren't they? Right? I mean, as you go to the right, you're getting bigger. Right? R is ordered as well by the same intuitive, this room respond, this looks a little bit, different though in the following sense. Let me ask you a question. What is the smallest positive? One, if I mean strictly positive, small positive, right? What is the smallest positive real number? There is, because no matter what comes out of your mouth, I will divide it by 2, right? You can always go, so this ordering, I mean, certainly if I give you any 2 real numbers, if I just give them to you, you can tell me which one's the bigger one, right? But if I say, what's the smallest positive one, go, exists, right? So these things can be strange. But let me ask you something. I think we can all agree with this. If I give you any 2 integers or any 2 real numbers, one of them is greater than or equal to the other, right? In fact, it works either way. So if I am silly to you and I give you both 2 and 2, 2 is certainly greater than or equal to 2, or less than or equal to 2, right? Any 2 integers, any 2 real numbers that I pick, I can compare. Let me give you another way to order things. Actually, I don't want you to think of this numbers. Let's just. Well, A is just a set of numbers. To power set of this. I'm going to set all subsets. So I've got the empty set. I've got the singleton subsets. I've got the subsets that have, oh, look at me. I'm supposed to put X, Y, Z in there, sorry. I've got the singleton sets. I've got the subsets consisting of 2 things. And then I've got the whole track. Would everybody agree that that's the power set, I would call it? Now, let me show you something here. I am going to declare S and T in the power set of A. I'm going to declare that S is less than or equal to T if and only if S is contained. This seems like a reasonable thing to say, right? I want to say that S is littler than T if S is contained in T. Right? Let's kind of take a look at the situation here. That's the daddy Mac. That's the biggest subset, right? I've got some other subsets. Two levels say. Now, I am going to draw a line from big to small. So this is what these lines mean. This is greater than or equal to this, right? Because it contains this. I agree so far? Where do I draw the line from this? This, X and Z, don't I? This is Y. Now, actually, let me appeal to you again here. Would everybody agree that this is transitive in the following sense? If S is contained in P and T is contained in R, then S is contained in R. That's true for subsets, isn't it? Right. So I don't need to draw. So for example, if I was really being super careful, I would draw a line from here down to the empty set, right? But since there are arrows leading down here, this is greater than or equal to this, which is greater than or equal to this, which is greater than or equal to this. Right? So I don't want to put too many lines in there and confuse you. Well, what's different about this ordering, right? So this one's the alpha dog. This one, it's bigger than these three. But what's different than this than say the ordering we talked about on the integers and the real numbers? Yes.
There are like, in each level, there are multiple, right, elements. So like X, C, and Y, C, X, Y are they're all less than X, Y, Z, but they're not greater than or less than each other, nor are they equivalent to each other.
Okay, that's probably even more subtle than I'm gonna say something that's probably a little bit not as subtle here, and that is there are apples and oranges, right? In the following sense. Set doesn't contain this one. This one doesn't contain this one. This is different than what we're used to in the real numbers, right? Because what happens in the real numbers, I give you any two real numbers, one of them's less than or equal to the other. And what I mean by apples and oranges here is there are some apples and oranges. You can't compare this apple to this orange. Notice that this and this, you can't compare this. This was not contained in here, even though this has more elements than this one. This one's truly not smaller because it's not contained in there. This is the kind of order where you can't always compare things. We're going to talk more about this later. This is called, as you might guess, a partial order, because even though you can compare some things or some things you can't. Okay, good place to put for today. Any questions? All right. We'll see you on Wednesday.